Welcome everybody to my video series on probability and statistics. I am Dr. Lathram, and you can usually find me in the Department of Mathematics at Missouri Southern State University. So let's get going on today's topic of histograms and characterizing data. So you may already know what a histogram is, but let's start off with a definition that tries to capture what the fundamental features of it are. So a frequency histogram is going to be a graphical representation of a data set. We take an interval in which is going to be big enough to contain all of the elements in our data set D. We then take that interval and subdivide it into non-overlapping subintervals, I sub 1, I sub 2, all the way up to I sub n. So we've got divided up into n subintervals. And then we have this function m. M is going to be a map from our collection of subintervals into the real numbers. And what this m does, it counts, or it actually measures the number of data points that fall in that subinterval. Typically, what we might have if we describe this mathematically, m of I sub k, so I sub k is our kth subinterval. We do a sum over all of the elements in our data set of the characteristic function of I sub k evaluated at the data point. So what this thing is, this just kind of gives us a fancy way of counting how many data points actually fall in the interval I sub k, or if we take that same function and normalize it by the number of data points that we have the relative frequency of the number of data points that fall in a particular interval. So if you want a description of actually what the indicator function does and how it's really defined, a pretty good description of that is given by the Wikipedia page, and I give the web address to that right here. So now we've seen the theoretical description of what a histogram is. Now let's see how we would actually do one. Let's see what it looks like whenever the rubber meets the road. So what we start off with is a data set. So your data set's going to contain probably a whole bunch of numbers. So you're going to look at whatever the smallest number is that shows up. You're going to look at whatever the largest number that shows up. And you're going to take that range, and what we do is divide that range into non-overlapping subintervals. So here's our I sub 1, I sub 2, I sub 3, and so on and so on. And then all we do is to say, all right, I'm going to go back over to my data set. I'm going to just count how many of my data points actually show up in a particular subinterval. And that's going to give me a list of counts for every single element. And so the reason for the intervals being non-overlapping is so that we don't end up counting our data points twice. So each data point is going to show up in one and only one of our subintervals. So our total number of counts, if we add them all up, should equal our total number of data points. So then what we do is to form rectangles. So we've got one rectangle for each subinterval that we have. So each rectangle represents one subinterval. And then the height of that rectangle is going to correspond to the number of counts that we have. So it's going to be, so the highest rectangle is going to be the largest number of counts that we have. And that is essentially what a histogram is. It gives you a visual representation of what the structure, kind of the counts of how this data set is divided up. So now we've seen that with our histograms, we're just dividing our data range up into subintervals and counting how many data points fall in each subinterval. And so that seems like a pretty simple, easy idea. But then when we start to do that, if somebody just walks up to us and hands us a data set, question would be, where should our boundaries be for our intervals? Second question how many intervals should we use? And those are two really good questions. And the answer is there is no real definitive answer. We do have some guidelines that can help us out in trying to answer those questions, but there's no really concrete answer to how you do that. One guide is that the endpoints of our intervals should be chosen so that it's really not likely, or it's even impossible, for a data point to fall on the boundary. That if we take a boundary and include it in one adjacent subinterval, but if we change it and put it in another adjacent subinterval, then we don't want that to influence the shape of the graph very much. So if we've got lots of data points falling around that interval, we don't really want to choose that as a dividing point. And so in order to kind of maintain the stability and the shape of our graph, we don't want our data points to really fall on our boundary values. Second thing, probably we span our data set with anywhere between 5 to 20 subintervals. Could be more, could be less, but in general, 5 to 20. Usually the more data that you have, larger number of subintervals are going to be okay. And there are algorithms that have been developed for choosing the number of subintervals. In the R statistics program, we've got options such as the Sturgis algorithm, Scott, and the Friedman-Diaconis algorithm. We won't go into any of the details as to what those actually do, but they just let your data set kind of decide how many subintervals to use. So let's get our hands dirty with a little bit of data and an actual problem. So the price to earnings ratio, so the PE ratio of a stock, is the ratio of a stock's most recent price per share to the stock's earnings per share, averaged over a 12-month period, multiplied by 100. The PE ratios for 44 securities selling at earning multiples much higher than the average market price are given in a data set. Use R to construct a relative frequency histogram for the data. Now the data set, you can find the data at this website listed below, and the data is for exercise 1.2.R data. Alright, so let's start by firing up R. So we type R, get it loaded. So now let's go to the directory that contains our data set. So let's set our working directory to experiment, to histograms. And now let's see if that's where our data file is. So we can list files in that directory. And sure enough, there's our data, exercise.1.2.R data. So let's load that data. So load exercise 1.2.R data. And now let's see what variables that we have listed in our workspace. So if we type ls open parentheses, close parentheses to see what variables we have, we've got the variable stock. And so if we type stock, we get a list of all of our data values. Now we can confirm we're supposed to have 44 of those. So let's see if we do the length of our stock variable. Sure enough, that has 44 data entries in it. And so now, let's see what a histogram. So R is a wonderful program. It's got functions built in for you. So if we just type hist of stock, that will draw a histogram for us. So let's move that down. What does our histogram look like? So this is what a frequency histogram drawn by R is going to look like. So we've got the frequency of counts, we've got our bins. In this case, we've got 1, 2, 3, 4, 5, 6, 7 bins. So 7 rectangles. So the height of our rectangles, like we've got about a little over 30 in the first bin, maybe around 5 in the second bin, 2, maybe 3 in this third bin, fourth bin. And so that is going to give us a graphical representation of what our data looks like. But if we want a little bit more, more concrete information about our histogram, then we can actually make our histogram a variable on its own. So if we say stock hist, and let's say that is the histogram hist for stock, then it will save that histogram data in a variable on its own. So that's actually a data structure. So inside that data structure, we've got different entries. So if we type stock hist and then a $, and then if we hit tab, that will tell us what values we've got inside this data structure. Okay. So it looks like we've got values of breaks, and counts, density, mids, the x name, and equidistant. Okay. So let's see what each kind of information we've got in each one of these. So if we do stock hist of breaks, then that's going to tell us what our bins were for our data. So our bins, remember that we've got our stock hist, our bins look like they were from 10 to 20, 20 to 30, 30 to 40. Sure enough, when we do our breaks, those give our boundary values for our breaks. If we do stock hist counts, that actually gives us the number of counts that we've got in each one of our bins. So in the first bin we had 32, in the second bin we had 5, third bin we had 2, 3, 1, 0, and 1. Okay. So I'm going to skip density for a little bit. We'll come back to that. If we do mids, then what mids is the midpoint of each one of our intervals. So we've got a midpoint of 15 in between 10 and 20, midpoint of 25 between 20 and 30, midpoint of 35 in between 30 and 40, and so on. So mids actually gives us our midpoints of our intervals. Xname is the variable that we used to draw the histogram itself. So that's the data set that we used to draw it. Equidist is a variable that tells us that each one of our bins was going to be of equal size. So how far apart those things were, equal distance between them? Yes, they were. There wasn't anything in our definition that said that our subintervals had to be the same size. So in this case, R did use the same size intervals, and so that variable was just a Boolean value that comes back either true or false. In this case, true, since they were all the same size. Okay, so we were asked to draw a relative frequency histogram. So how might we do that? Well, let's go back up to our stock hist. If we wanted a relative frequency histogram, then we would we'd add on one requirement. So tell R that do we want a frequency histogram equal to false. So freq equal F tells us that we do not want a frequency histogram, we want a relative frequency histogram, and so the picture that it draws is this. So notice that the picture is pretty much the same. Our bins are staying the same, same shape for everything, but the vertical column is now a density. It's not a frequency, it's going to be a density. So let's see what that might be. So let's save our new histogram as a variable, and then examine the elements in the data structure again. So now if we look at stock hist, we still have the same values in the data structure. And so if we do breaks did not change. Our counts did not change. But now let's look at the value of density. So density, we get a bunch of values, and so we know that our counts actually tell us how many counts that we've got in each particular bin. Well, we know that we've got 44 data elements. So if we do our stock hist counts, and then if we divide that by 44, let's see what values we have. So dividing by 44, we get values of 0.727273, 0.0727273, 0.11363636, 113636, 4545455, 4545455. So we're seeing the same values, but the difference being that the values in our density are a factor of 10 less than the percentage of counts that we have in our bins. So why is that the case? So what is density actually giving us? Well, the idea in the density is that the frequency of elements inside one of these bins is going to be equal to the area of that rectangle. And so the area of the rectangle just being base times height, well, we've got a height of the actual density value. So for the first rectangle, we would have a height of 0.0727273. And then, so if we take the height of that times the length of the base, well, the length of the base is 10. So 10 times that height, sure enough, does give us our frequency of points inside that particular bin. And so that's why those values are going to be a factor of 10 different than our frequency of counts that show up in that bin. So hopefully this has given you a little bit of an introduction to using R and developing some histograms. If you want more information or you want to look at the help page, then in R you can just type $hist, and that will give you the help page to give you more details about some of the variables that you can change for the histograms to customize them however that you like. So hopefully this has been informative, and I will see you guys next time.